Okay. So the first thing we want to talk about is we want to talk about acid bases. Okay. So this should be reviewed to you guys because we have gone over this in Chem 123. The big thing we want to talk about is the pKa values. Okay. So what are pKa values? Well, pKa values describe how acidic something is. Okay. Or it's the acid dissociation constant. So what does that actually mean? If we think about a K value is essentially the ratio of the products to the reactants. Okay. So now that we have this, we also know that we can have our sort of equation here with the concentrations, and it'll look something like this. And this is if we have an equation AA plus BB goes to the product CC and DD. Okay, so when we say pKa values, we actually want to think about which side is the equilibrium going to lie on. So if we were to draw out sort of a diagram here and we had a products and we had a reactants, this would be K is equal to 1, okay? Which means that we're perfectly balanced between the products and the reactants. Okay, sorry about the background noise. There is going to be a bit of background noise as we go through this because my mom's cooking in the kitchen. So now if we see K is greater than 1, so if this is 1, K is greater than 1, we're actually going to lie towards the product side. And if K is less than 1, we're going to lie towards the reactant side. Okay, does that make sense for everybody? Just let me know in the chat. It's all good. Okay, so when we talk about the Ka value, it's basically going to be how likely it is if we start with a reactant. Let's say, for example, phenol, how likely it is to go to a product where it loses its proton. Okay, so this is what we call the acid, and this is the conjugate base. Right, so all of this should be reviewed right now. And what we want to see is that pKa, there is an inverse relationship. So pKa is basically negative log of Ka. Okay. So this means that, for example, if we had a Ka value of 10 to the negative 3, when we take negative log 10 to the negative 3, this is going to equal 3. And if we have a Ka value of 10 to the 5, we would have a negative log 10 to the 5, which is equal to negative 5. Okay, does that make sense? So if we compare these two Ka values, we're actually going to have 10 to the 3 is, 10 to the negative 3 is less than 10 to the 5. In fact, this is quite small. This is a very small decimal, and this is quite a large number, right? However, we'll see that 3 is greater than negative 5. So the key thing we want to see here for pKa's, the lower the number, the more it favors the products. Okay, so just looking at an example, let's say we had this, and let's say its pKa was about 5, and then we compare it with this, and let's say its pKa is about 26. Which one would be more acidic? So if this is the left one and this is the right one, which one would you guys say is more acidic? Just let me know in the chat. Yeah, so I'm seeing some left here. What are the other people in the chat? Just let me know. L, perfect, nice. Yeah, perfect. So yeah, it's going to be left. And the reason why it's left is because the lower the number, the more acidic, okay? So the key thing you want to see with pKa's is the lower the number, and that includes negative numbers, the more it's going to favor the products, okay? Okay. So given that that's the case, when we take something like the hydronium ion, this has a pKa of -2. We're going to form a conjugate base, which is water, right? Water is neutral, and neutral things tend to be more stable. And because this pK is -2, we're actually going to expect that this form is more stable. So generally, when we have this hydronium ion, it actually wants to give away a proton, right? Remember, a acid is a proton donator, that's the Bronsted-Lowry definition of an acid. Okay, so what we're going to see with hydronium, this is what we call a hydronium ion. This hydronium ion is going to want to give away its proton so that it becomes neutral as water. However, what we'll see is that if we have a stronger acid, for example, HCl, this is a stronger acid, and it's going to want to give away its proton, so it'll actually force it into its hydronium ion state. Does that make sense? Okay. So how can we determine this if there are two pKa's, right? Let's say there's two things fighting against each other. Right now, we can kind of just see, okay, these sort of things. What if they're fighting against each other? Okay, so this is a little trick I like to use. So let's say we have A plus B, and we're fighting between C and D. Okay, and we say that pKa of A is equal to -5, and the pKa of D is 3. So this would mean that the conjugate base of C, the conjugate base of A is going to be C. So this is the conjugate base. Conjugate base. And then for here, this would be the acid, right? Because the thing with the pKa is the acid. And then this would be its conjugate base. So just looking at this right now, do you guys have any idea which side the equilibrium will lie on? You can just give a guess in the chat. Okay, so I see one person saying products. Any other? Does anybody else want to take a guess? Okay, yeah, so that is a good guess. And it is correct, right? So we actually are going to lie to the products in this case. And if you think about rationalization of pKa's, this one is a lot more acidic, so it's going to want to push the reaction to this side. Now, there is a cool quick trick I like to do, which is to take the right side pKa, right? Notice how this is right. And so we'll take the right-hand side and we'll subtract the left-hand side. And if it's positive, it'll lie to the products. If it's negative, it'll lie to the reactants. So in this case, we take 3 minus -5, which is equal to 8. And 8 is a positive number, so it's going to lie to the products. Okay, so if we did another example, for example, if we had a pKa of -5 and we had a pKa of like -3, so this might be a bit more ambiguous. What we could do is we could just take -5 minus -3, and this is equal to -2. So this would still lie on the reactant side. Does that make sense? So here's a quick little trick you can do, which is the right-hand side minus the left-hand side, and then we just look at the sign of it. If it's positive, it goes to the right, and if it's negative, it goes to the left. Okay. So in terms of this, we know that we have the definition of the acids and bases. So we'll just quickly go over that definition. So when we have a Bronsted-Lowry acid, just call B for base. This is going to be the Bronsted-Lowry acid towards something that looks like something that's water. And this is going to be the conjugate base. Now, water can actually act as a base or an acid, but the key thing here is the Bronsted. So Bronsted, is it EAD? Oh no, it's just ED. Okay. Bronsted acid it's going to be a proton donator. Okay. And the base, if we think about a base, for example, so we have, maybe we'll do HCl. And again, we're going to use water. Now we form a conjugate acid. Now this is what we're going to call the Bronsted base. Bronsted base. So you guys know the difference between the proton acceptor and proton donator, right? Just let me know in chat if that's clear to you guys. Cool. Okay. And now what we're going to do is we're going to relate this to acidity / basicity. So these things are really related. And the key thing you guys want to look at in 233 is resonance and stability. Whenever a professor is going to ask you something, generally the answer is going to be resonance or stability, some form of those two things, and you need to come up with an answer. So I'm going to give you guys an example. This is a very common question on Chem 233 exams, so just keep this in mind. I'm pretty sure this is in almost all of the practice exams. So what you're going to do is you're going to be provided with two structures, and you're basically going to say that I don't know the exact pKas here. This one, I think it's like 10, and then pK, I think 16. So don't take my word for it. These aren't exact pKa values, but basically the question is asking, this one is more acidic. Why? So why is the left structure more acidic? So does anybody in chat have any ideas? The question is asking why is the pKa lower? So in this case, we know what the pKas are, right? So we know that it is more acidic, but why is it more acidic? So we're asking for a rationale or explanation. Does anyone have any ideas? Okay, if nobody has any ideas, no worries. We're gonna go over this and the conjugate. Oh, perfect. There we go. Right. Yeah, exactly. So these are two answers which are correct, right? The charge cannot be distributed. So whenever you have these kind of questions, what you want to do is you want to draw the conjugate base. And remember, to draw the conjugate base, we remove the proton. Versus, okay. So notice how here, what we're going to see is that we have this negative and it can actually stabilize via resonance. Resonance and aromaticity, right? Because this is not a regular type of resonance, it's a aromatic resonance. And we'll see that we can move it again and et cetera, and we're basically going to have more resonance structures. So this charge is actually going to be delocalized around the ring, whereas here we can't really push it anywhere. Does that make sense? Just let me know in the chat. So whenever you have these type of questions, the first thing you want to do is, for example, if you're talking about acidity, draw out the conjugate base And then we can rationalize, maybe using resonance, maybe using whatever, that, oh, okay, look, this negative charge is going to be delocalized throughout the ring. So that means it's going to be more stable. Okay. So now what we're going to do is we're going to compare another thing, which is we're going to have this alkyne with a pKa, I believe this is about 26 versus pK of this, which is going to be, I believe it's like 40 or something, quite high. Isn't the more unstable one the stronger acid? Yes, exactly. So remember what we're looking at here. These are the conjugates. So the conjugate base is more stable, which means the acid is stronger. Okay. And the reason why is, if you think about it, in chemistry, everything wants to be stable. So if we draw out this right one, we'll see this, for example, this is going to be the energy difference, which is going to be more stable. So we can see that this is going to be our phenol. Starts as the products, sorry, it starts as the reactants, and then we end with the products being more stable. But if you look at the other one, maybe it looks more like this, and it's not that much more stable. In fact, I might even argue that it's less stable. So it would be like almost like fighting an uphill battle. So we have something that looks like this. Okay. So what we do actually in chemistry is we look at the products and see, we come up with a rationale for, okay, if the products are more stable, that would make sense because you want to get to something that's more stable. So you are completely right that the more unstable one is the stronger acid. So if you think about this in terms of more unstable, that makes sense. But normally we talk about the products when we're talking about stability because we want to get to the more stable thing. Does that answer your question? So let me know in the chat. All right, perfect. Okay, so now we're going to look at these two. Oops. And what we're going to see right off the bat is we have a huge pKa difference. And these two things are quite similar. There's just going to be three carbons. There's nothing really sort of prevalent here that we can see is creating the difference. So what we're going to do again is we're going to take off the proton. And so we take this off, and then we have a negative charge here. This negative, and we have a negative like this. Okay. So just looking off the bat, this is a very hard one, by the way. So I don't know if you're expected to know this right off the bat, but it will be on the test as a question, possibly. So does anyone have any ideas why this is actually going to be more acidic? Anyone has any ideas, just put it in the chat. Cool, yeah, it's actually going to be due to hybridization. So if we look over here, this is an sp3 and this is an sp hybridization. When we think about hybridization, sp is going to be 50% S, 50% P. And if we think about here, we have sp3, which is going to be 3 Ps. It's going to be 25% S and 75% P. Now, what we're going to do is we're going to draw the structures. And if we draw the structures, sorry, the orbitals. So if we draw an s orbital, it looks something like this. And if we draw a p orbital, it looks something like this, right? Okay. So just looking at this, we're going to have a cloud of negative electrons, negative charge. And whenever in chemistry we have a negative, we want it to be close to positive. This is going to be nice and stable. So if you think about a nucleus in an s orbital, the nucleus is going to be a plus charge. So we want our negative charge to be closer to the nucleus to be able to stabilize it. However, if we look at the p orbital, the nucleus, you can't actually go to the nucleus because there's a node there. So the negative charge is actually going to be further away from the nucleus. Okay. So what we'll see is that when something has more S character, it actually becomes better at stabilizing, negative charge. Okay, so if you're asked these kind of questions where maybe there's no resonance, there's no aromaticity, it's just sort of by itself, we want to think, okay, it has to do with S character hybridization. Okay, that's another common question that's asked in the exam as well. All right, now what we're going to do is we're just going to do a quick review of aromaticity. And remember, there's going to be 3 rules for aromaticity. So the most common example is going to be the benzene. Right off the bat, anytime you see something with a benzene, you can just straight up say it is aromatic. So if we have some weird stuff here, maybe some random substituents, this is an aromatic system because we have this group, which is the aromatic benzene. Okay, so what are the rules to determine if something's aromatic? The first thing is it needs to be in a ring. For example, if you have something that looks like this, this is not aromatic because it is not in a ring and it's not conjugated. Well, it is conjugated, but it's not conjugated in a ring. So it's a ring system, which is planar. So what does planar mean? Well, planar basically means if you were to lie it down flat on a sheet, it would just go on that sheet flat. Okay, and how do you know something is planar? Well, notice we can think about the hybridization. If we have sp2, this is basically going to be planar because we know that sp2 is trigonal planar. So it's quite in the name. So we have to search for sp or sp2. Okay, and there is a fully conjugated system. So let's talk about what a conjugated system means. So this is a conjugated system. And this is not conjugated. Let me draw this a bit more clear. Okay. Why is this not conjugated? Because right here, there is a break between the connections. So when something is conjugated, it basically means that it's adjacent. And if we were to draw out the pi orbital, the p orbitals, it'll make a lot more sense. So I'm going to draw out a benzene. So notice how if you have this benzene, we can actually draw a bond here. We can draw a bond here. We can draw a bond here. Oops. And what we can see is that if we were to actually sort of switch the bonds, we could actually draw a bond here. We could draw a bond here, and we could draw a bond here, right? So this is kind of like the resonance kind of thing, where it goes here, and it goes here. So this is what we mean by a conjugated system. The pi electrons are sort of able to share with each other. However, if we draw this one, I'm not going to draw the whole system. I'm just going to draw these carbons. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. What we're going to see is that we have a bond here. Oops. We have a bond here and we have a bond here. And what we're going to see is that this one isn't even a sp2. If you think about this atom, we have 2 hydrogens sticking off of it. So does anybody know what hybridization this atom is going to be? sp3, perfect. Right, so it's going to be an sp3 sort of tetrahedral geometry carbon, right? So it's not even going to have that sort of empty p orbital there, right? So this means it's not going to be able to share, like this is too far for it to share. So whenever you're looking for conjugated systems, it has to be 1 adjacent over, okay? 1 over. Does that make sense? And then lastly, the last sort of rule, So this is rule 2. This is conjugated. And the last rule is the Huckel's rule, or 4n plus 2 pi electrons. 4n plus 2 pi electrons. Now, n has to be an integer. So if n is equal to 1/2, for example, you have 4n plus 2, and we say, okay, let's say n is equal to 1/2. Then we have 2 plus 2 is equal to 4. This is not aromatic. In fact, it's actually called something called anti-aromatic, but that's another thing. But because it's not aromatic, for it to be aromatic, n has to equal an integer. So this is not allowed for aromaticity. Okay. So what we can do is let's go over a quick example. And what we want to talk about quickly also is the localization of electrons. So what we want to see here is if we draw this one versus this one. Okay, so if we take a look at these two structures over here, the question you want to ask is, okay, are there any lone pairs that aren't drawn? So remember, with carbons, everything is implicit. And then with the other sort of elements, there may be lone pairs which are not drawn in. Nitrogen, notice how it has no formal charge here, and the valence of nitrogen is 5. So if we think about the formal charge here, it's going to be 1, 2. So we have 1, 2, 3, 4, 5. So 5 minus 5 is equal to 0. That's good. Now over here, though, again, we have lone pairs, which should be 1, 2, 3, 4, 5. 5 minus 5 is equal to 0. That's good. Everything is satisfied. So there are, however, a difference between these two electrons. Okay. So right now, just straight up looking at the two structures, can anybody tell me what the hybridization of this nitrogen is? Let me know in the chat if anybody knows. Yeah, no worries. So, okay, it's actually going to be sp2. And what we're going to see is, okay, it's sp2. So these electrons are going to be localized there. And what I mean by localized is they can't move around. They can't participate in resonance. And if you think about why that's the case, we're basically going to have our orbital here and sort of this other spot for electrons. It's actually going to be a trigonal planar shape. Does that make sense? It's going to be a trigonal planar. Okay. And if you think about how those electrons are there, they can't actually move or resonate into anywhere else. However, if we look at this nitrogen, what we're going to see is that if we move it like this, we're actually going to make it into something that's sp2. Okay, so now we have an sp2 nitrogen, and this sp2 nitrogen is actually going to be sp2. So we actually have a delocalized electrons. Does it make sense? So whenever we're thinking about electrons, we want to think about whether they're localized or delocalized. And generally, when they can participate in resonance, such as this, we'll call them delocalized electrons. So technically, the hybridization of this nitrogen is actually going to be sp2. Okay, so this is a small caveat that you guys want to watch out for. Whenever we have an sp3 structure, check out if there can be resonance to make an sp2 structure. Therefore, it's going to be actually sp2. Okay, I'll go over a quick example of this. If we think about an amide, so remember this functional group is called an amide, right? Amide. You would guess that this nitrogen has a sp3 hybridization, but actually it's going to have an sp2 hybridization. And how we can determine this is, again, by drawing resonance. And we'll see that now it's become trigonal planar, it's become sp2. So this is actually an sp2 hybridization. Okay, so whenever you're working with figuring out aromaticity, watch out for this sort of localization or delocalization of electrons. Okay, but straight off the bat, we're going to count here. Is this aromatic? The answer is going to be yes. Why is it aromatic? Because we can, well, let's just go through our rules, right? So first of all, is it a ring? Yes, it is a ring. Is it planar? Well, this is sp2, 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 sp2. It's all sp2. It's planar. The second thing, is it a conjugated system? Well, yes, all these pi bonds are adjacent. So yes, it is conjugated. Conjugated. Okay, and then lastly three, what we're going to do is we have the lone pairs on the side. Are these lone pairs actually included in the pi system? No, they're not, right? Because we talked about it. If we're sp2 already, we can't go down one more level, right? So when normally we see, okay, we have sp3, we can go to sp2. Well, we don't normally see many cases where we're already in sp2 and then we go down to sp, right? So being that the case, we know that these electrons are not part of the system. So how many pi electrons do we actually have? We have 1, 2, 3 times 2, so 6 electrons. And according to Huckel's rule, for n plus 2, n is equal to 1, so it is aromatic. Okay, we're going to go through a sort of weird example here and sort of see something important. So right off the bat, we'll look at the first one. These bonds are not conjugated, right? Because there is something in the way that's not adjacent, right? So the double bonds are not adjacent. So this one straight off the bat is out. And if we look at this one over here, we have 1, 2, 3. But notice how this pi system is actually outside of the ring. So if we were to draw these top carbons, notice how the pi bond actually exists outside of the ring. So it actually breaks the ring. And what you can see is with our sort of pi system, we have our pi system over here, pi system over here. It is actually going to break the pi system. Notice how the pi system wants to sort of connect in a ring. This breaks the pi system. So you can think of it like this is the circle, and then this actually is going to break the system. So this is not a ring, okay? And so this one's out. So now we just have to test the other two. And straight off the bat, we would look at this. Okay, this looks all sp2, that's good. This is all sp2, that's good, that's planar. So let's think about Huckel's rule here. We have 1, 2, 3, 4, 5. And we're going to have 5 electrons, so it's going to be 10 electrons. And if we use Huckel's rule, 4n plus 2, n is equal to 2, so that's good. And then we have 1, 2, 3, 4, 5, 6, 7, 14 electrons, n is equal to 3. So both are actually, we would expect both to be aromatic, right? However, there is one caveat to this, which is very tricky. This is the aromatic one, this is not aromatic, okay? And you might be wondering, okay, that's really weird. This follows all of the rules, so why isn't it aromatic? Well, it's because there's one rule that it secretly doesn't follow. And what we're going to do is we're going to try to draw it in a page here. So we're going to try to draw it planar, and we're going to see something weird happens. Okay, so we'll see that we have this, this, and then remember each carbon is going to actually have a hydrogen. And you can already see our problem here. If the hydrogens were in the plane of the page, they would be bumping into each other, right? So looking at it from the top, these hydrogens would bump into each other. So what we're actually going to see with this structure is it's actually going to have to bend a bit, and it's not going to be planar. So this is not planar. Okay, this is one of those very tricky exceptions. Sometimes they like to put these kind of questions onto exams, sometimes they don't. But just keep that in mind where there may be something really small about it that tricks you up. Okay, so the reason why this one is not aromatic is because it is not planar. Okay. Does anyone have any questions regarding that? Just let me know in the chat. How is 3 planar? Okay, right. So if you draw this one out, everything is, so if you think about this one, if you think about all the hydrogens, first of all, this is all sp2. So all of the hydrogens, you draw them accordingly. Notice how there's actually going to be enough space for all of the hydrogens. So it doesn't actually interfere with each other. So it actually ends up being planar. This is a very hard sort of caveat to look out for, a red herring. They tend to not put this on the exam unless it's very, very sort of, they really want to lower the curve. But I'm just letting you guys know just in case. If you're, for example, you're split between 2 options like this, where this one is very obviously not, this one's obviously not, but these 2 we both seem aromatic, you want to draw some sort of rationale. Okay, maybe it's not planar. Maybe it's not conjugated or something like that. Okay. We have less than a minute for this meeting. So what we're going to do is I'm going to restart the meeting and then you guys can rejoin because I'm using the free trial of Zoom right now. So I'm just going to quickly restart the meeting and then you guys can rejoin in like 10 seconds. All right. All right. BRB, I'm just going to reset the meeting. Just let me know in the chat. Okay, cool. All right. So what we want to talk about is we want to talk about the dominant forms P at a given pH. So this is a very common question and it will guaranteed be on your OChem exam. If it's not on your first midterm, it will be on your second and it will be on your final. So what we're going to do is we're going to draw an amino acid. One second here. And a dominant form basically means how's the amino acid going to look like at a given pH. So we have an NH3 plus, and we have okay. So this we'll call a pKa. We'll say it has a pKa of around 1.82. And the next one, I'm just going to copy and paste it. Okay. And then we're going to draw a different structure because notice how there's a lot of groups on here. There's some acids, there's some bases, there's all a bunch of different groups. And we want to think about how these different groups interact. And we'll see that this carboxylate group is actually going to be in the second structure, and it's going to be a pKa of 6.04. Okay, so the question is now what they're going to do is they're going to ask you at a given pH of some pH number, what form is it? So there might be multiple. In this case, we're only dealing with 2, but we'll call this the form A, and we'll call this the form B. So is it going to be form A or form B? Okay. And I think there actually is another structure. Let me just quickly draw that. So I'll just paste it in. And the last structure that we're going to work with is just going to be this one. Okay. And this is going to be form C, and I believe, okay. So what we're going to do is we're just going to solve this question. What we're going to do is we're just going to isolate one of the groups, the carboxylic acid. And we're going to see the point where it changes from here to here is going to be 1.82. Does that make sense? Because it goes from being an acid to its conjugate base. And we know the pKa means that it's going to lose its proton. Does that make sense? So what we're going to do is we're going to draw a number line. And it was going to be 1.82. And notice how before 1.82, right? So it's less acidic. It's just going to be the COOH. And then once we cross that threshold, now it's strong. It's more than 1.82. It's going to be more basic in that condition. So it's going to steal away the proton, and it's going to look like this, right? Then now we have our next one, which is going to be 6.04. And we're going to see the thing that it gives up is it's actually going to be giving up this proton. So what we can do is we can just draw an NH plus. And once it crosses 6.04, it actually becomes an N. Does that make sense? Okay. So what we're going to do now is we're basically going to ask, okay, at a pH of 3, what is the form? The dominant form. So to answer this question, all we have to do is we have to draw 3. 3 is in the middle of 1.82 and 6, and we're going to have these two things. Okay. So in fact, this will end up being a dominant form. Does that make sense? Is that clear to everyone in the chat? Okay, good. So this is how we solve the dominant forms question. Generally, what you want to do, it's very easy if you just draw a number line. If you can kind of do it by hand too and kind of see it, that works as well. I like to draw the number line so I don't really make any mistakes. Okay, so you can do like a before and after. So this is before and this is after. Okay. So have you guys gone over hydrohalogenation? So let me know in the chat. No. Okay. Not yet. Okay. So I think we have covered most of the stuff that you've covered so far, except for SN1 and SN2, right? Okay. I don't think we have gone over this last concept either. Oh, okay. So I think I've gone a bit ahead. So let's just don't worry about this for now, not for now. Not for now. Okay. So don't worry about this too much for now. I think I went a bit ahead. So this will come up, but it is an important concept. So just keep it in the back of your mind. You've talked about carbocation stabilities, right? Have you guys talked about carbocation stabilities? Just let me know in the chat. Okay. So real quick, if we think about carbocation stability, we have a primary carbocation, we have a secondary carbocation, we have a tertiary carbocation, and then we have something, for example, that's like allylic. In terms of stability, which one is the most stable here? What do you guys think? Anybody want to give it a go? Last one, yeah, perfect. So in terms of stability, we're actually going to go this way. And remember how I said in Chem 233, the big answer is actually going to be resonance or stability. And so this one is actually going to be resonance. So that makes sense. But between these ones, why are they more stable? So we're going to quickly talk about that. And we'll see that the only difference is we have more methyl groups. Okay, and what do methyl groups actually do? I'm going to draw a quick diagram here. We draw sort of our plus sp2, and then we have our this is going to actually be our methyl group. And notice how it can actually donate electron density through those bonds. And this is what we call hyperconjugation. So this is quite a big word, but all you have to know about hyperconjugation is that the methyl groups are electron donating. So they actually give a bit of electron density to the positive carbocation. And notice how here, the more methyl groups we have, the more of the donating effect we have. Therefore, it's more stabilized. Does that make sense? Okay, so generally in Chem 233, you're basically never ever going to see these. A primary carbocation and a methyl carbocation. Just this is a no-go. Don't do this. If there's something with a primary carbocation, that oftentimes that's telling you something's wrong. Let's not do that. Okay. So this is the key thing with hyperconjugation. And then now, with our last bit of time, I'll quickly talk about the SN1 and SN2 reactions. And then I don't think you guys have gone over E2 and E1 yet. So if you guys are interested in attending the future sessions, we will be going over that as well. But for now, we'll just go over SN1 and SN2. So what we'll see with SN1 is if we have, for example, a bromine leaving group. And we have a bromine leaving group again. And then we have some sort of nucleophile, maybe it's going to be water. This will actually form two products. And we have AOH. So does anybody know what these two products are called, how they're related to each other? These two things are enantiomers. Yeah, exactly. So these are enantiomers. And when we just do the SN2 pathway, we actually only get one product, which is going to be the inverted product. So the thing we want to understand in OChem is you always want to be asking the question, why does a certain thing happen? So you want to ask yourself, okay, why is it that when we do SN2, we're left with one product, and when we do SN1, we're left with two products? And the reason being is because the SN1 pathway, how it works is, let's draw this out. We have a Br leaving group, which will actually form a carbocation. And if you think about it, there's actually an H here. And if you think about this, this is sp2. So if we draw it, we have our positive here, and we have our orbital. So if you think about where the nucleophile can attack from, so in this case, the nucleophile is going to be H2O. It's actually going to be able to attack from the top, or it's going to be able to attack from the bottom. Okay, so notice how if it attacks from the top, we're going to be able to get this because it's coming out of the page. And if it attacks from the bottom, it's going to look like this, which is going to be into the page. So that's why we get enantiomers. Does that make sense? So let me know in the chat if that makes sense. And then if we think about the SN2 pathway, SN2 is a lot more sort of aggressive. It is actually going to come in and kick out the current partner or bonding group, just like that. So for that to happen, if you think about it, here's our Br, for example, and then we have our hydrogen. It actually has to come in from the other side to kick out the Br. And then now the H is out front and the attacking group is in the back. Okay, does that make sense? So the difference between SN2 and SN1 is SN1 is stepwise. And it goes through a carbocation. And SN2 is concerted. And concerted basically means in one step and no carbocation, but it has Walden inversion. And what is Walden inversion? Well, it's just going to be the change of the stereochemistry like we see here. Okay. And the key thing you want to see about SN1, because notice how we have this positive charge. Generally, when we see positive charge, this is going to be a acidic environment. And generally, when we see sort of a negative charge, this is a basic environment. Okay, that's the sort of key distinction we have there. So for example, if you saw a reaction like this, and we had NaOH, for example, would you predict this to be SN1 or SN2? SN2, perfect, right? Because this is a basic environment. Okay, so that's how we sort of are going to determine, okay, is it SN1 or SN2? For example, if we had H2O and maybe HCl, this is a lot more, much nicer conditions for SN1 to happen. So this is going to be SN1. Okay, so those are the two main key distinctions of SN1 and SN2. You will get to more detail when you start to talk about the differences between E1 competition and SN1 competition and SN2 and E2 competition. Okay.